Right, so good morning, everyone. My name is Torsten Dudda. I'm working in Ericsson Research, and I will present the perspectives from the 6G ANA German research project on the 6G radio access. Brief introduction to our project. So 6G ANA is the 6G Lighthouse research project from the initiative, the 6G initiative, 6G platform of the German Federal Ministry of Education and Research, BMBF. Coordinator is Nokia. It's a 3-year project. We are now halfway through. You see here an outline of the work packages. So we look into use cases and architecture, system design in the work package 2, and that is the main focus of the presentation today. We look into the 6G access. That's also the item that Ericsson is coordinating. Then there are more work items, work packages on networks of networks and automation and simplification. And then also one more on proof of concepts development. Regarding the project partners, so we are 34 partners, quite a strong consortium from industry, SMEs, research institutes, and universities. Yeah, basically from partners all over Germany here. And what I will present next is basically also what the partners contributed here to work package 2. So let's have a look at that. Focus 6G access, maybe one more breakdown of what is included in this work package. So we have 3 tasks: access overview, interworking on spectrum usage. There we look into a breakdown of the use case requirements towards the access, the RAN. Look also into spectrum options and migration solutions towards 6G. The second task is about PHY. So here we look into flexible, secure, and harmonized PHY, into, for example, programmability of the physical layer, inclusion of AI, distributed MIMO, and also physical layer security. And then the last one is here on RAN protocols and cloud-based architecture. The overall target is to provide concepts and concept proposals for the 6G radio access to make it more energy efficient, keeping flexibility for implementation, making it reliable and secure. And in the coming slides, we will go then into some of these concepts that we discussed in the project for this second and third task, so for PHY and protocols and architecture. And maybe we start here with our architecture vision. So we see here different functions within the Cloud RAN. And these functions in the Cloud RAN, they can be implemented or instantiated in a more distributed on-premise cloud, or also being more centralized far edge cloud, for example. For example, the physical layer. A physical layer can be, as a function, also being instantiated with different instances, one that is more energy efficient, for example, and one that is more spectrally efficient. That's the idea here of this adaptiveness. The radio resource management, RM, there we can have different instances, for example, per resources, like a carrier, a cell, or a subnetwork. UE control with the radio resource control and access slicing can be applied there as well. And when it comes then to the user plane and the user plane stack, there slicing can also be applied. There can be one stack that is more optimized for latency critical services and one more for mobile broadband services. Good. Continuing then and starting a bit with the fundamentals of the physical layer. What do we have in mind here? First of all, we see both evolutionary and revolutionary aspects of the physical layer for 6G. We need to consider that 6G will support also the 5G use cases, but also new ones. 6G will also use the 5G spectrum. Actually, it is to utilize the spectrum full range or parts of within the range of 450 megahertz to sub-terahertz. So there, for these use cases and spectrum where 5G is already strong and has mature features, there we see evolutionary aspects of 6G, comprising then these mature 5G features, for example, like OFDM as the baseline for the waveform. But there are revolutionary aspects as well, where we see some breakthroughs and new and special designs. For example, when it comes to the scalable support of massive mobile XR devices, or integration of AI techniques into the physical layer, MIMO and massive distributed MIMO, and then also specialized waveforms are probably needed for special aspects like sub-terahertz communication, joint communication and sensing, zero energy devices, or wake-up radios. Yeah, and as mentioned before, the physical edge should also be adaptive to have options. For example, different radios or radio options that can be chosen according to the situation that we are in at the moment. One radio might be more spectrally efficient, but another one more energy efficient. And that's then considered, for example, in this gearbox PHY concept, which we further develop in this project here as well. Good. Continuing then, distributed MIMO and very large arrays is also a key topic in the project. So we look here into cell-free massive MIMO, so basically distributed MIMO that is user-centric to meet the high capacity demands, for example, for this mobile XR use case, where the demands are on the capacity are very strong. And we are evaluating here basically the trade-offs of having this more distributed deployment versus more traditional centralized deployment architectures. We need to consider there that all these individual, let's call them access point or antenna points or transition points, their hardware consumes energy. We need to look into algorithms for an efficient power control. There's the fronthaul between the central processing entity and these access points. That comes with requirements and limitations. Yeah, and to control all this, we are looking into different algorithms here. Another interesting topics are very large aperture arrays. So this can be seen as an enhancement of MIMO technologies. So these very large arrays, they lead to an interesting effect of expanding the near field, basically, and we get then near field propagation effects that we need to consider. And the potential advantage of exploiting these effects of the near field is to allow also multi-user MIMO along the depth dimension. So this is illustrated here in the picture below. So our objective here is to understand the propagation characteristics of the near field
Sorry,
better.
Torsten, something happened with your slide sharing, so the slide disappeared.
Okay. Strange. I will just share again.
Yeah, visible now.
Okay, all right. I think someone else grabbed the screen for a moment. That might be the reason. Very large aperture arrays was our topic on this slide. To allow basically multi-user MIMO along the depth path. Not sure if you saw that yet, so it's illustrated here a bit in the lower picture. Our objective is to understand better these characteristics of the near field, because this is still in early research phase. And we also then look into transmitter algorithms to steer that, these kind of beamforming or spot beamforming for multiple users. Good. Okay, continuing then. Integration of AI and PHY. There we look into a couple of examples of how AI could help in the physical layer. Within the general framework of a neural network receiver, we're looking into the example of integrating a deep neural network for channel estimation. Looking there, we see there are some performance gains. For example, we could also reduce the number of pilots being sent by having then the trade-off of having a more complex receiver based on AI here. Yeah, and that's basically what we need to evaluate, to analyze these trade-offs, more complexity versus the performance gain or signaling reduction we can get. And we are looking there into further scenarios also. So here the graphs are a bit more from a non-MIMO scenario, but what if we use MIMO? This is still up for research. Another example is AI in PA digital post distortion. So the power amplifier that operates more energy and efficient in its nonlinear domain, but this leads then to signal distortions. And these need to be mitigated. Traditional methods would do that at the transmitter side, but for the uplink direction, the transmitter is the UE, and these methods could become quite complex in the UE or too complex and costly for the UE. The idea is here to move this post distortion to the receiver side and based on AI, learn and compensate the non-linearities. Yeah, and there we're also up for quantifying gains versus complexity. Good. So then another topic that a couple of partners look into from the project is the physical layer security and how it could complement traditional security methods. Traditionally, we have at higher layers cryptographic methods to secure the communication over the air. but the physical layer properties could also be utilized to complement that. There are different things that we look into here. For example, how to utilize the wireless channel properties, make the communication more secure, basically. So there is an inherent secrecy rate or secrecy performance in that wireless channel that could be utilized and could even be improved by also reconfigurable intelligent surfaces on the path. Other examples are to use the physical propagation channel for authentication. So it's quite unique between transmitter and receiver. The properties of it could be utilized. And further aspects are to ensure hardware integrity, for example, by analyzing the physical channel properties along a path and deciding then based on them whether there was a tampering in the hardware that could be found out, and thus the hardware integrity could be ensured. Good. Okay. Continuing then with layer 2, going beyond the physical layer. 6G protocols. So here our target is simplification of the protocol stack. The user plane protocol stack in 3G, 4G, 5G consists of PDCP, RLC, and MEC. And we are looking here into methods to simplify the stack. This would lower the operation cost while maintaining the flexibility, and that's the target, maintaining still the flexibility we have, for example, to handle diverse QoS traffics in 6G. And one interesting aspect there is to look into how we can pre-process packets that are coming in and how we can effectively online process or process packets that are going out of the protocol stack. For example, when scheduler decides for transport block size and the data is put into the radio frame and transmitted. There are key functions that we look into. These key functions are quite general for all radio protocols. We need security over the air. We need adaptation of packets to frames, segmentation, for example, retransmissions in case of forward error correction failures. And there, for example, we see at the moment 3 different layers that do retransmissions. We have the HARC layer and MAC. We have RLC layer correcting HARC errors. And then for handover situations, we have retransmissions on PDCP even. And the question here is how this can be maybe organized in a more effective way. Active queue management, we would like to keep the buffering that we have in the protocol stack sufficiently large so that we can always transmit and don't run empty, but we would like to also keep the latency, so the buffering, as small as possible. Yeah, and to balance this, we need a more active or more fast active queue management that is able to indicate congestions based on ECN marking, L4S, faster as we see it right now. This has an also relation with how reordering is done and also how retransmissions are organized. Good. Mapping them, these different functions, to our functional architecture proposal or vision. We see here then in the user plane that we have PDCP, which can do pre-processing of incoming data with security, header compression, and the handover anchoring. And then the more, let's call it online processing, so synchronous to scheduler and framing on RLC with its buffer management, segmentation, retransmissions, and reordering. And on MAC with the multiplexing of different flows, HARC protocol, and also support for carrier aggregation there. Good. Another topic is radio resource management. So we are looking into different aspects of the radio resource management for 6G. So there are some different proposals on the table and being discussed. One example area is the subnetworks area. As you probably know, subnetworks is a concept where we have a network within a network. The subnetwork is a short range or localized mobile cell to support the extreme requirements within that local area. So for example, low latency in an in-factory or in-vehicle use case. If we have multiple of those, we need to coordinate the interference between the subnetworks, so inter-subnetwork interference. And that's a challenge because we assume these subnetworks to be mobile. This channel is uncertain. We are thinking about dense deployments here, and we have then typically these use cases or traffics with a low latency demand. So there we are looking into different management schemes, mostly in the frequency domain. So basically it's about how to divide the radio resources among the subnetworks. And it can be distributed hybrid or centralized approaches. And we're looking into them. Before the management of the interference.
Torsten,
yes.
Could you also soon come to a conclusion? Thank you.
Yes, in a moment. Before the interference management, first of all, we need to estimate the interference as well to be proactive here. And there we're looking into data-driven methods like long short-term memories and federated learning. Last slide, so that we are right on track in time. We're looking into further aspects of the radio resource management. Non-orthogonal multiple access is on the table here, NOMA schemes, allowing then a low latency access to radio resources and also compute resources that we might have in the radio. Contention-based uplink access, also to lower the latency for initial data transmissions. There we're looking, for example, into schemes that integrate also a switchover from this contention-based access for initial packets to more effective, efficient dynamic scheduling. The 6G platform is also seen as a platform that is not only communicating or providing communication, but also other means, for example, gathering information about spatial characteristics or positioning of the environment and the devices. And thus, it might be interesting also to consider this information, spatial characteristics, in the scheduling, the radio resource management. So we could consider them enrichment information. And also in radio resource management, the integration of AI is an interesting topic that we are looking into as well. Scheduling of power, resources, different UIs, MIMO channels, and so on is a very complex problem. There, AI could play in a role, and we are looking also into that. One example here is the V2X scenario, platooning, where we look into how resources could be provided, centralized, distributed, or federated learning could be applied there. As a brief conclusion, so we saw some perspectives of what we are doing on the radio access in the 6G ANA project, the German 6G Lighthouse project, and especially what we do there in the work package 2. We looked into flexible and secure PHY, simplified RAN protocols in the Cloud RAN architecture, and radio resource management techniques. And if there are any questions, please just contact me. I could also point you to our project publication here on the right side, or you could have a look at the individual publications that we listed in the slides for further info. I'm saying that explicitly because our deliverables are actually not public. Information is available through these publications. Thank you.